So in an oxidation-reduction reaction, we're looking at electron transfers. So sometimes they're just called redox reaction. That's the short term. We want to look at ionic compounds usually, because ionic compounds are ones that are stealing electrons from other atoms. Their atoms are stealing electrons, so electrons will be transferred a lot easier. We will write out some half reactions. So we'll have this total reaction, and then we're going to look at the compounds that are oxidized and reduced, and we're going to draw or write out two separate reactions for that whole reaction. So oxidation reactions, we lose electrons because in order to be oxidized, the oxidation number goes up. In order to have an oxidation go up, you have to lose negative charges, so you'd lose electrons. Reduction, the oxidation number must go down. The oxidation number is reduced. In order to make the oxidation number go down, you have to add more negative charges, so you've gained electrons. So it's kind of opposite, backwards thinking again. And the reagents are the elements that are causing the change in oxidation number. So the reducing agent is the element that's donating the electrons to the atom that's oxidized. The oxidizing agent is the element that's accepting the electrons from the atom that's oxidized. So the reducing agent is the atom that's doing the reducing. It's causing the atom to be reduced. The oxidizing agent is the atom that's causing it to be oxidized. We'll look at some examples. So if we look at this equation, we have two magnesium ions. Where's the whole? So here would be our equation. And the element that is being oxidized is magnesium. Let's assign oxidation numbers here. Oh, you can't see the bottom equation. Let's write it up here. No. Is that right? No, there's no 2 down here. There, that's the equation that we can't see. So what would be the oxidation number for magnesium? Here. It's in its free elemental form, so it's 0. How about this oxygen? 0 also. It's in its free elemental form. It's not bonded to a different atom. Now, here we know oxygen is -2, so then we bring down 2, +2, and +2. We don't have to put in the coefficient. We don't worry about coefficients. So, magnesium is going from 0 to +2. Has the oxidation number gotten bigger or smaller? Bigger, so it has been oxidized. Oxygen's oxidation number has gone down. It's been reduced. The oxidation number is reduced. So the oxidation half reaction, we look at the element that's being oxidized, magnesium, and we just show what happens to just magnesium. Magnesium goes from this free elemental form into a magnesium ion, and it has lost 4 electrons because each magnesium is 2+ and there's 2 magnesiums, so we've lost a total of 4 electrons. Oxygen has gone from 0 to -2, so this is the reduction half reaction. It took those 4 electrons that magnesium lost, and each oxygen then took 2, which is why we become a 2-, and there's 2 oxygens. So then they just wrote out all of the ions, everything with the electrons. The electrons basically cancel out because you lost 4, gained 4, and you get this final equation. So there's 5 different common redox reactions, and we'll go through examples of each of them. Combination or synthesis, decomposition. Well, what do you think in a combination or synthesis reaction, what happens?
Something's made.
Two elements combine to form one thing. So 2 things combine to form one thing. What about decomposition?
One thing splits into 2 things.
One thing splits into 2 or more things. Single displacement, you're going to have just a single element plus a compound, and they're going to switch spots. It's kind of like at a dance if someone cuts in and you switch partners. Okay. Double displacement. I had a professor that said this way. Well, it's like what we've done before, where you have a compound plus another compound, and they switch spots. If you think of it like you went to a dance and you had these 2 partners and these 2 partners, and then they switch partners for dance. And then combustion. What is combustion? Fire. You're burning something. What do you have to add in order to burn something? Oxygen. So you're adding oxygen. So in this synthesis reaction, we already said they have 2 or more substances combining to form another compound. This is just a generalized equation. So let's look at these 2 synthesis reactions. So we're going to get, what are we going to get for our product here? Most likely SO2. So now let's look at which one's oxidized, which one's reduced. So what's sulfur's oxidation number here? 0. It's in its free elemental form. What about oxygen? 0. Now we have to figure out these are, let's sulfur, or oxygen is -2, makes this -4. So sulfur must be +4. So which element was oxidized? Sulfur is oxidized in this case. Which one is reduced? Oxygen. How do we figure that out? So if it's oxidized, it means the oxidation number must go up. So sulfur has gone from 0 to +4. It's gone up. Oxygen, to be reduced, you have to have the oxidation number go down. Oxygen's gone from 0 to -2.
So can you do what TK just said? Like if they're both zeros on the left side and it goes to the right side, can you just assume that the positive number element is oxidized and the negative number element is reduced? Like you can just
Yeah.
+4 -2.
Mm-hmm. Yeah. Now, the other terminology that we went through is which one is the oxidizing agent? So the oxidizing agent has to, let me write that, must cause the element to be oxidized. So in order for sulfur to be oxidized, it had to give its electrons to someone, to an element. So it gave its oxygens to oxygen. So oxygen is the oxidizing agent. The reducing agent, it must cause the other element to be reduced. So oxygen is reduced. Where did it get its electrons? From sulfur. So you can see they're opposite, kind of. The oxidized element is the reducing agent. The element that's reduced is the oxidizing agent. Questions? So how about this next equation? What are we going to get for a compound? No. Magnesium has what charge as an ion?
2+.
And nitrogen is 3 minus, so we're going to have Mg3N2. There you go. The reason why we didn't have to do that on the top one, look at the charges, because sulfur and oxygen are both negative ions, so they're just going to combine together. Magnesium and nitrogen is a cation and anion, so we need to cross the charges. So these are both 0 again, because they're in their free elemental form. Nitrogen, we said, was -3. We know nitrogen's -3. They're single elements as ions. So nitrogen's ion charge is -3. Magnesium should end up being +2, but let's go through. So we get +2.
How do you know that it should be +2?
Because it's just a single atom as an ion. So magnesium and nitrogen are both single atoms as ions. They should have the same oxidation number as their ion charge. So which one is oxidized? Magnesium and reduced. Nitrogen. Which one was the oxidizing agent? And the reducing agent? The zeros, because they're in their free elemental form. When they're by themselves, not bonded to anything else, they're always 0. Any atom is 0. Okay, I think I want to stop there. That's a lot of information for you. So we were on decomposition. Basically opposite of synthesis, where a single compound reacts to produce 2 substances. A lot of times you have to heat this. So that's where that triangle, you may see the triangle above the yield sign, because you're heating it. That's just the general equation. So energy is added as heat or electricity usually. So if we have this compound breaking up, we're going to get mercury and oxygen separate. So we'd have Hg plus O2. Is it balanced? We need a 2 there, right? So now to figure out if it's oxidized or reduced, we need to figure out oxidation numbers. So here, we'd have oxygen is -2. So we'd have -2 down here. This needs to be +2. So +2. And then what would the oxidation number be for mercury on the product side? 0. Yep. It's in a free elemental form, so it'd be 0, and oxygen is also 0. So if the element's oxidized, its oxidation number has done what? Increased. So which one increased? Oxygen, right? Oxygen went from -2 to 0. So its number increased.
So then,
Hydrogen went from +2 to 0. So this would be,
and so oxygen is the reducing agent and mercury is the oxidizing agent.
yep. Oxygen is the reducing agent. Mercury is the oxidizing agent. I think on your worksheet, it asks for just the oxidizing and reducing agent. If you need to go through and figure out which one was oxidized and reduced first and then figure out which one was the agent, that's fine. However you go about that. Mm-hmm. Only if they're in their free elemental form. So for decomposition, probably, because they are breaking up into usually. Yeah. Let me think. Okay, this one though, we're going to split into this. So both of them are not going to be 0 this case. I should have cleared. Hold on. Let's click that. And for this one, since it's not splitting up into just the 2 elements, they would give you that KCl as one of your products or something like that. Yeah. Nope, we just got to balance it. I don't know if that's 2. That 2 is right even. Yeah, it would be, right? Because we need a 3 here and then a 2 here. Yeah. So oxygen is -2. Potassium, in this case, since this is chlorate, potassium is the single ion. So this would be +1. That's what its ion charge is. So chlorine must be +5. But with the potassium, the bottom needs to be 0. If it was just ClO3 with the -1, then it would need to be equal to -1. Then let's figure out the left side, or the right side. Potassium chloride, again, this is +1. So this is -1. And oxygen is 0 by itself. So now we have 3 elements we got to check. Has potassium's oxidation number changed? So it's neither oxidized or reduced. It's not any of those. Which one has been oxidized? So which number has gone up? Oh, the oxidation number increased. And reduced? Yep. Chlorine went from +5 to -1. Okay, next here. So single replacement reaction, sometimes called single displacement. One element replaces a similar element. The similar element means a cation replaces a cation, or an anion replaces an anion. A cation does not replace an anion, because we don't want 2 cations bonding together or 2 anions. So cation replaces cation, anion replaces anion. If you have a replacement of a metal, the more active metal will replace the least active metal. So in this case, aluminum is more active than the lead, so it's replacing lead here. Let's figure out which one's oxidizing. Let's figure that out for that aluminum problem. So what's the aluminum's oxidation number here? 0. It's in its free elemental form. How about here? Lead is our single element. So this, but it's lead 2. So it's +2. Oxygen is -2, which means that's there's 6, 12. So that's plus 10. So at plus 5 for an oxidation number. How about lead? Lead's gone from, is now 0, right? And aluminum is the single element, so now it is plus 3. Oxygen is negative 2, so now it's negative 18. Which means this has to be 15, and then plus 5. Ooh, in this case, oh, no, we have one. So has aluminum changed? So aluminum is oxidized. And lead is reduced. How about nitrogen and oxygen? Neither. So they aren't either. Okay, for this one, we're going to get hydrogen. So sodium is replacing hydrogen because that is the cation, the positive ion. So we're going to get hydrogen gas plus sodium oxide. Oops, that should be Na. Na2O. So sodium's oxidation number is -2. So +1 for hydrogen. How about hydrogen on the yield side, on the product side? 0. Oxygen is -2 again. +2, so +1. So which element has been oxidized? Okay. Na is oxidized. And reduced. Is there another one underneath that?
Yeah.
What is it? So what are we going to get? Chlorine is what as an ion? It's an anion, so it's going to replace the anion. So we're going to replace Br, so we're left with Br2 plus KCl. This is going to be -1, so +1, 0, -1, so this is +1 also. So which one is oxidized? And reduce. Chlorine, right? Chlorine's gone down from 0 to -1. Potassium hasn't changed. We always have those two. Okay, then double displacement, or double replacement. We're going to have ions of 2 compounds exchange places in aqueous solutions. So we've dealt with these before, and the molecular compounds precipitate reactions. A lot of times you may see a formation of precipitate, which is the insoluble compound. We've seen that already. There. And And the last type of reaction is the combustion. We already said if you have a combustion reaction, you have to add oxygen. Usually you release energy in the form of heat or light. And if you combust a hydrocarbon, so hydrocarbons just have hydrogen, carbon, and then they can have oxygen. So hydrogen, carbon, oxygen. They don't have to have oxygen. But whenever you combust a hydrocarbon, you always produce carbon dioxide and water. So this is an example, burning propane. You'd have propane as C3H8. So you add oxygen if you're burning it. And then since C3H8, propane, is a hydrocarbon, it only has hydrogen and carbon in it, it will always produce carbon dioxide and water. So you would have all your reactions and products written out, and then you'd just balance it after that. And so one thing you will need to use is the activity series when you have a single displacement. When we were talking about the most active and least active metal, that's based on the activity series, and the most active element will be on top. So the activity series is on page on page 114. I don't like that one as well. So the most active metals are on top. So anything that is on top, this little chart, so lithium is on top, it will replace any of these metals in a compound. If you would find, like, cobalt is trying to replace magnesium, cobalt is not able to replace magnesium because cobalt is lower on the activity series than magnesium. Magnesium could replace cobalt, but cobalt cannot replace magnesium. So use that chart on page 114, and let's see if these reactions will occur. So aluminum is trying to replace zinc and zinc chloride. Can aluminum replace zinc? Yep. Could. Aluminum is trying to replace zinc. Is aluminum higher than zinc? It is. So we will get a reaction. So we would want to write out zinc plus, then aluminum chloride is AlCl3. And they've already started balancing this. So we must need a 2 here and a 3 here. 3, 3, 6, 6, 2, 2. Yep. Okay, the second one, cobalt's trying to replace sodium and sodium chloride. Is cobalt able to replace sodium? No, because cobalt is lower on the activity series, so you could just write no reaction. So that's how you would use that activity series. No reaction. And so these are using our activity series. Let's just see if we're going to have a reaction. So zinc is trying to replace what? Trying to replace magnesium. Can it replace magnesium? So zinc has to be higher. No? Okay. So there'd be no reaction? How about aluminum's replacing hydrogen? And if you look off to the side, it says it reacts with steam to reproduce H2. Is this steam? How do we know it's steam? It's a gas. So we are going to produce H2, and then aluminum oxide would be Al2O3. So we're going to need a 3 here and a 2 here. That gives us 6, so a 3 here. Now cadmium plus oxide, there must be something off to the side by cadmium. Is there? Because this isn't a single displacement reaction, is it? What kind of reaction would this be? This would be a synthesis. So what would we synthesize here? Cadmium oxide. Cadmium has what charge? +2, and oxygen's -2. So it's just CDO. We need a 2 here and a 2 here. The last one, iodine. Is that a cation or anion? Anion. So is it going to replace potassium or fluorine? Fluorine. So we're going to get fluorine. Actually, let me think about that. For anions, if you look down the row of halogens, that is your activity series. So fluorine is higher than iodine. Can iodine replace fluorine? No. So there's actually no reaction there. So for your nonmetals, your anions, it will usually be your halogens, and so you just use that row of halogens as your activity series. I think that's it, isn't it? Should be. Yeah, we aren't doing this yet.